Hi, this is Iman, and I want to talk about my project, which is about adaptive chase agent. The instructor is Dr. Shooting Neo from Computer Science Department of Bowling Green State University. In this presentation, I want to talk about the adaptive chess agent. And as you know, in the traditional chess program, uh, the program is highly dependent on the strategic, and calculations. But here, the AI project learned from each game, and then I talk about the deep impact of using AI in chess, uh, not only for advanced AI technology, but also for other complex decision making scenario. And then I go through the detailed examination of the adaptive chess agent, focusing on how it adapts and evolves through gameplay. The goals of the project, this project aims to develop an AI chess agent that surpass traditional chess engine. And as I mentioned, uh, uh, the traditional chess engine, it depends on strategies and a lot of calculation, and the traditional engine cannot adapt or learn from their games, and uh, but the or agent can do that. And another thing is uses the control complexity of chess to test and refine AI technology, leveraging the game's deep strategic layers as an ideal testing ground. So, success in creating an adaptive AI for chess could indicate the potential for AI application in broader areas such as business strategy and decision making in ambiguous conditions. And here, the project seeks to advance the narrative of AI development by pushing the limits of what AI can achieve in a strategic game setting. About the problem statements, there are a lot of challenges with the traditional chess AI. And I mentioned that traditional chess AIs excel in computational power and can predict outcomes from past games, but they lack the nuanced understanding and adaptability of human players, especially against skilled or unconventional opponents. And also, there is a need for dynamic strategy adaptation. The dynamic nature of chess, characterized by its nearly infinite board configurations and the psychological complexity of human opponents, demands an equally dynamic approach to a strategy. So, the project aims to fill this need by creating an AI chess agent which is capable to learn from each move, each game, and each opponent. And we hope to fill this gap between the raw computational power of traditional AIs and the adaptive strategic depths of human cognition. About the related work and AI developments if I want to talk about AI developments in the chess, nowadays, uh, the evolution of chess AI is too fast, and the evolution of chess AI showcases significant milestone from Deep Blue defeating Guy Kasparov, which one of the big guy, the famous person in the chess, to Alpha Zero self-taught mastery. And About uh, uh, about the influence of literature, or I inspired by development in reinforcement learning with Alpha Zero, which developed by David Silvers, and also the foundational text on reinforcement learning by Richard Sutton and Andrew G. Bartow to design this project. And about the approach and methodology of the project, the foundation of our approach is a dual strategy. We have used adversarial search and reinforcement learning. We combine the predictive power of adversarial search with the adaptive capabilities of reinforcement learning. And about the adversarial search, particularly through the use of min-max algorithm and alpha-beta pruning, enables the agent to make informed decision by evaluating potential moves and their consequences or their outcomes. And this is complemented by reinforcement learning, especially Q learning, and its deep learning extension called DQN, which allows the agent to learn from outcomes of its actions and refine its policies over time. If I want to talk about min max with alpha beta pruning briefly, actually, the min-max algorithm, enhanced by alpha beta pruning, forms the core of uh, mm, our agent's decision making process in immediate gameplay context. About min-max by evaluating potential moves and their outcomes several steps ahead while simultaneously eliminating paths that won't affect the final decision. By doing this, this algorithm allows the agent to play significantly and effectively. About alpha beta pruning, it enhances the process by significantly reducing the number of nodes evaluated, making the computational faster and more efficient. About the software design, the software architecture of the adaptive chess agent is designed to smoothly integrate the adversarial search and reinforcement learning module. In the coding part, I will show how these components interact to guide the agent's decision making process. And this design not only optimizes performance but also ensures that the agent remain flexible and capable of incorporating future advancement in AI and machine learning. And briefly about main components, as I mentioned, the adversarial search module leveraging min-max with alpha beta pruning is tasked with evaluating the immediate consequences of potential moves, providing a solid tactical foundation for agents' gameplay. And at the same time, the reinforcement learning module utilizing QLearner and DQN focuses on the strategic aspects, learning from each game's outcome to refine the policy. And this dual approach actually ensures that the agent is equipped to handle the complexity of the environment. About the implementation, I have used Python as a primary programming language. And for doing this, I used NumPy for numerical computations, which enable us to efficiently implement complex algorithms and process the chessboard as chessboard states with high performance. And if we go through the code, here this is the code, and as you can see, I use chess, NumPy, and random libraries. And in this cell, uh, here I defined min-max algorithm for adversarial search to find uh, the best move. And here, uh, this is a class for uh, defining a chess agent. In this class, I combine all component together. And as you can see, I define states here, possible moves, actions, and here there is a definition how to update the queue table, and and then find a max for the updating the queue table. And here you can see the reward. For checkmate, the reward is 1, otherwise the reward is 0. And if you want, you can increase or decrease the reward for each of them. And for running the code, you just need to call the class and run it. And when you run the code, you will see something like that. If I open it here, and this is move, this is the first move, and the result of this game is draw, and you can see here, and after 233 moves. So if I want to explain some of these moves, I should go back to the slides. And for this example, the parameters set up like the depth of min max search as 3 levels, and for the exploration rate starts at 1.0 and decays by 0.995 per move. And for this example, the final result was draw after 233 moves. And this is the move one, and you can see for the first move is mostly is a random. And about here we have move 5, for example, and if we compare move 5 with before and after that, and we can see here the AI possibly explored a less typical opening move, pushing a pawn to influence maybe to influence the central later. And this could be random due to high exploration rate early in the game. And on the right side, you can see move 10, and highly any strategy starting to form here, such as controlling the center. And here for move 15, for example, uh, this move shows a shift from exploration now to exploitation, and where the AI uses learned values from previous games to decide on a piece trade, aiming to simplify the board. And for move 20, we can see how the AI manages increasing pressure or threats from the opponent, possibly leading to a defensive move. And here we have move 25th, and for 25th move, and here the AI prioritizes promoting a pawn, leveraging the learn Q values to maximize its chances in a simplified position. And about the final position, the last move, and if we want to talk about factors leading to the draw, and actually insufficient material left to conclude the game with a win, and an example of AI effectively neutralizing the opponent's threats. If I want to talk about the strengths and the weaknesses of the project, the weaknesses is about the effective use of Q learning model, and the Q learning model is designed to help the AI learn from every move it makes, gradually improving its ability to predict the most rewarding actions in different game states. A major strength in this instance is the AI's capability to navigate and often escape losing situations or to secure draws from complex and potentially disadvantageous positions. So if I want to talk about some strengths, we can talk about avoid repeating mistakes. The AI learns from past games, recognizing patterns that lead to losses or disadvantageous positions. And we can talk about decision making in critical moment, and but by evaluating various outcomes or consequences based on its Q table, the AI can make informed decisions that minimize risk. And also, the agent can handle the complexity of the environment. So these are the strengths of the project. About the weaknesses, despite the AI's capability to avoid uh, 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 losers games, there are areas for improvement, particularly in exploiting advantageous position more effectively. For instance, there is a problem with conservatism in strategy. The AI may overly prioritize safe moves over aggressive strategies that could lead to win, especially in a favorable position. Delayed response to opponent weaknesses. Sometimes the AI may not respond quickly or effectively enough to exploit an opponent's mistakes. And also, there is a problem with optimal play convergence. The AI, the agent, may not always converge on the best win strategy due to either limitation in its evaluation function or because of insufficient depth in its Q-learning updates. About future work, and we can for future work we can use advanced learning algorithm. The field of reinforcement learning is rapidly evolving and growing with new algorithms and techniques being developed that could further enhance the agent performance. And also with the adaptive exploration strategy by using uh, by developing more sophisticated exploration strategy, we can dynamically adjust uh, based we just we just adjust based on the agent performance, and the learning stage is another exciting area for future work. So and another thing that we can work on it by opponent modeling and human AI collaboration. And there is a vast potential in enhancing the agent's ability to model and anticipate opponents' moves and strategies. And we can use this kind of advanced algorithm to improve this project. And about the summary of key finding, the development of our adaptive chess agent represents a significant step forward in the application of AI to chess and strategic games in general. The agent's ability to learn, adapt, and improve over time underscores the potential of integrating advanced AI techniques into game strategy development. And impact of the project on AI research and game strategy development. This project contributes to the broader field of AI by explaining how adaptive learning techniques can be applied to complex environment. And about the final thoughts, I can say that it's clear that the journey of developing the adaptive chess agent has not only been about creating a competitive chess player, but also about exploring the possibilities of AI, the challenges encountered, and lessons learned along the way highlight the dynamic nature of AI research and its potential to transform how we approach problem solving and strategic thinking. And these are three references I used for this project. And thank you for your attention. I hope it was useful for you.